All right, on to 3.2. We're going to talk about derivatives of logarithmic functions. In order to talk about, or in order to prove what we need to prove regarding derivatives of logarithmic functions, we need to remind ourselves that the limit as x approaches 0 of 1 plus x to the 1 over x is e. We actually, the number e, right, like about 2.7. We actually gave a couple different limit definitions of the number e, and this was one of them. Okay, so using that fact, we can prove that the derivative of the natural log function is 1 over x, provided, of course, that x is greater than 0. If x is 0 or negative, then natural log of x is not even a real number. So we'll assume x is greater than 0. So the way that we prove this derivative is we apply the limit definition, okay? And we can factor out the 1 over h. We can use a property of logarithms, the quotient rule, to rewrite this as natural log of x plus h divided by x, okay? And then we can reduce that, right? X divided by x is 1. H divided by x, of course, is going to remain h divided by x. And now we do something kind of clever. We're going to do a little u substitution. We're going to say let u be h over x, right? We're going to let u be this thing right here. If that's the case, then h would be u times x, okay? Moreover, as h goes to 0, u is also going to go to 0. So making all of those replacements, this is what we get. So limit as h goes to 0 of 1 over h times ln of 1 plus h over x, which is what we left off with, is now going to become limit as u goes to 0, because remember, as h goes to 0, u goes to 0, of 1 over u times x, because remember, h is u times x, okay, times the natural log of 1 plus u, because remember, h over x is u. From there, we can factor out the 1 over x, and then we can move this limit inside. Sorry, no, I'm getting ahead of myself. So we can factor out the 1 over x, then we can use another property of logarithms to rewrite this coefficient as an exponent here. And then we can move the limit inside of the natural log, because as we've discussed in the past, the natural log function is a continuous function, right? So we can move the limit inside of here. Now this limit is familiar, right? This is this thing up here, or sorry, this thing up here, right? So it's just equal to the number e. Okay, so this is going to be 1 over x times the natural log of e. Well, natural log of e is just 1, okay? So that's 1 over x, and there you go. As kind of a corollary to that fact, the derivative of any logarithmic function of any base b is going to be 1 over x times natural log of b, okay? And the proof of that just relies on us using a change of base to rewrite log base b of x as natural log of x divided by natural log of b. 1 over natural log of b is just a constant that we can pull out, and then we're just left with the derivative of natural log of x. So this is 1 over natural log of b times 1 over x, which you can put together to get the statement that we had originally. Okay. So that's it for the proofs. Let me give you some examples of this stuff in action. Okay, so let's differentiate. Y equals ln of x squared plus 1. Okay, so the derivative y prime, or you could call it dy dx if you prefer. What we're going to say y prime is, well, natural log, it's 1 over this stuff, x squared plus 1. But then don't forget your chain rule, right? Because this is a composition of the natural log function and another function inside of here. So we've got to multiply this by the derivative of the inner function. So this would be times 2x, okay? Or in other words, we could put the 2x up here, 2x over x squared plus 1. And there you go, right? That's the derivative. Okay, let me give you another example. Let's do y equals natural log of x squared sine x over square root of 1 plus x. Okay, now on this one, before I differentiate, I'm actually going to use some properties of logarithms to make this a little bit simpler. You could differentiate the way it is. You could call this 1 over x squared sine x over square root of 1 plus x, and then times the derivative of all this stuff, which is going to require some quotient rule and then a product rule within a quotient rule, and it's going to get really ugly. But you could do it that way. However, I'm just going to rewrite this, and I'm writing y, not y prime, because I'm just going to rewrite the function. I can rewrite this as ln of x squared sine x minus ln of square root of 1 plus x. And in fact, I can take that a little further. Call this ln of x squared plus ln of sine x minus ln of 1 plus x to the 1/2 power. And just to make it a little bit, take it one more step and make it even easier, I'm going to call this 2 ln x plus ln of sine x minus 1/2 ln of 1 plus x. Okay? So far I haven't done any calculus. This has all just been algebra. But let's do some calculus now and take the derivative. Okay? So y prime is going to be 2 times 1 over x plus 1 over sine x times derivative of sine x, which is cosine x, minus 1/2 times 1 over 1 plus x times the derivative of this inner function, which in this case is just 1, so it doesn't change anything. We can clean this up a little bit. This is 2 over x plus cosine x over sine x minus 1 over 2 times 1 plus x. And if you wanted to, you could rewrite this as something like 2 over x plus cosine over sine is cotangent x. And you could distribute down there in the denominator. I'm not sure where the book is going to stop on this. I think I'd be inclined to maybe stop. Well, this is actually a nice answer. So there's that. A nice challenge for you would be to just differentiate this without rewriting it first. Okay, so just differentiate first and see if you can arrive at this same answer. My guess is that would require a lot of algebra to get there. But you should be able to, right? You should be able to if you differentiate first and then sort of like simplify it to try to get down here. Maybe it's super easy, I don't know. I'm not going to do it. Let me give you one more example. Now, this one is really simple, but it's going to illustrate something important. So let's do y equals natural log of negative x. Okay, so y prime is going to be 1 over negative x times the derivative of the inner function, which this time is negative 1, so be careful with that, right? But check out what we get, right? 1 over negative x times negative 1, this is just 1 over x. Okay, well, so that's interesting, right? Because on the one hand, we know that d dx of ln of positive x is 1 over x. We just proved it a second ago. And then on the other hand, we know d dx of ln of negative x is also positive 1 over x. So putting those two things together, what we can really say is this: natural log of absolute value of x is going to be 1 over x. Okay. Okay, so let me give you an example of that. And maybe I should say, this is assuming that x is not equal to 0. Okay, if x is equal to 0, then first of all, natural log of 0 is not defined, and second of all, 1 over 0 is also not defined. Okay, but for any other real number x, natural log of absolute value of x is just 1 over x. So So to sneak in another example there that kind of corresponds to that idea, let's calculate d dx of ln of absolute value of sine x. Okay, so d dx ln of absolute value of sine x. Well, we know that the natural log of the absolute value of x, the derivative of the natural log of the absolute value of x is just 1 over x. So the derivative of the natural log of the absolute value of some function of x is just going to be, well, 1 over that function of x without the absolute values. And then we have to apply chain rule, so we have to do the derivative of this inner function sine x. Derivative of sine is cosine, right? So this is cosine x over sine x, or if you prefer, cotangent. Okay, so that's kind of nice. Now, we can exploit natural logs quite a bit along the lines of something like part B. We can make things a lot easier by taking natural log of both sides before we differentiate. Let me show you what I mean. So let's use logarithmic differentiation. Whoops, sorry, you couldn't see what I was writing. Let's use logarithmic differentiation to find dy dx if y equals x squared times the cube root of 7x minus 14 over 1 plus x squared to the 4th power. Okay. Now, we don't need to use logarithmic differentiation to do this. We could just find the derivative directly. It would require us to use some product rule, some quotient rule, some chain rule, right? And it would get quite messy. So I'm going to follow the instructions then and use logarithmic differentiation, and you'll see that this becomes a lot easier. So here's how we use logarithmic differentiation. We start off by taking the natural log of both sides. Right? So I'm going to say, if y equals all of this junk, then the natural log of y equals the natural log of all of that junk. Okay. And now we can exploit all of the really nice properties of logarithms to make this thing a lot simpler. So this is going to be natural log of x squared times the cube root of 7x minus 14 minus the natural log of 1 plus x squared to the 4th power. That's natural log of x squared plus natural log of 7x minus 14 to the 1/3 power minus natural log of 1 plus x squared to the 4th power. And then we can use then we can use the power rule for logarithms to rewrite it as 2 ln x plus 1/3 ln 7x minus 14 minus 4 ln 1 plus x squared. And now calculating the derivatives is much easier. Keep in mind, this is the natural log of y. This is not y, it's the natural log of y. So what we're going to do is we're going to use implicit differentiation now. Right? So I'm going to take the derivative with respect to x of both sides of this equation. And let's see. So derivative of natural log of y is going to be 1 over y chain rule times dy dx. And then on the right hand side, where we can take the derivative of all this stuff now. So it's going to be 2 times 1 over x plus 1/3 times 1 over 7x minus 14 times 7. Right? So it's 1 over this stuff, and then times the derivative of this stuff, which is just 7. And then minus 4 times 1 over 1 plus x squared times 2x. Okay? Again, it's 1 over this stuff, and then times the derivative of this stuff. Let's see if we can clean that up a little. We've got 1 over y times dy dx equals 2 over x plus. I'm going to put the 7 up in the numerator and the 3 down in the denominator. We could really factor out a 7 actually. Oh yeah, we can make that a lot nicer. Well, maybe in the next step. 4 times 2 is 8. I'm going to call this 8x over 1 plus x squared. Okay, now we want to find dy dx though. So what we've found right now is 1 over y times dy dx. So dy dx, to find dy dx, we're going to multiply both sides by y. Right? So we say dy dx equals 2 over x plus, now here I'm going to cancel off the 7's, right? That should be a 2 now. So we have 1 over 3 times x minus 2. It's a little nicer. All this times y. Now y is this mess up here. So I'm just going to replace y down here with this stuff, and then I'll be done. If you wanted, you could distribute that 3x minus 6, I guess. Whoops, minus, sorry, 8x over 1 plus x squared times x squared times the cube root of 7x minus 14 over 1 plus x squared to the 4th power. And there you go. Okay. So a slightly, well, probably not slightly, I think it's probably a lot nicer way to differentiate this thing. Because like I said, otherwise you're going to be using quotient rules, a power rule within the quotient rule, a couple of chain rules within that. I mean, that's really complicated, but if you can use logarithmic differentiation, it's much nicer. So that's what you should get there, and that's all I have to say about derivatives of logarithms for now.